Hello, I'm going to talk about the relatively straightforward sheet 4 in section 2 of my Formalising Mathematics course. Here it is, here are the questions. They all kind of have one-line answers. I don't really want to edit the questions themselves, so let's start by section 2, the reals. Let's copy sheet 4 there and let's paste it here, there we go. And now let's write the solutions on the fly. So this teaches you about two very high-powered tactics, the library search tactic and the linearith tactic. So this is the kind of, once we start doing mathematics, we're doing things like sequences and tending to limits, and you're going to need to know basic facts about how to manipulate absolute values. And we've seen the tactic norm num before. And norm num does solve that goal, but there are other ways to do it as well. The library search tactic will tell us norm num is a tactic, but you see the library search tactic has told us a name of the theorem. You see this solves it as well. Let's hover over this. Abs neg. If alpha is some kind of object that has enough structure for this to make sense, then abs neg says the norm of minus a is the norm of a. So one could solve this tactic by using abs neg. It's an equality, so we could also rewrite it. Rewrite abs neg. We'll probably turn the left hand side into the right hand side. There you go, and that solves it as well. Because after norm minus x is turned into norm of x, the rewrite tactic tries refl. So there's several ways of doing that first one. And similarly here, at some point we'll get to the end of norm num's ability. Does norm num do this? You see, norm num can't solve this one. The norm num tactic is supposed to be normalizing numerals, and there's variables in this, so norm num isn't really the right tactic to be using. The issue is this is a theorem that's going to be in Lean's maths library somewhere, and so we can try searching for it. It's a sufficiently natural, natural claim. It looks like a sort of a useful result, and so there we go. I click on try this, and it replaces the call to library search with the lemma that's being used. So abs sum com. So again, you just hover over it, and you can see it says that a minus b equals b minus a in some kind of generality. If we have some linear ordered add group. So there you go. So that's how one would do this one. This one, max AB. Yeah, this is. You see, another way. Maybe I should mention this. I'm looking at if I was faced with wanting to find this, I would start guessing what this is called. This says the max of something is less than or equal to something. So I would do rewrite max LE. That's not quite that, is it? It's max LE. You see, this is the list of all the. So maybe I should tell you what I did there. I typed rewrite max LE, and it suggested a few things. For some reason, not that many things. And then I hit escape, and then I hit control space, and now this is listing every single thing in the library that sort of mentions these characters max LE. You see various things. The L and the E not even next to each other here, but it sort of gives you the best hits first at the top. And max LE, there's some sort of implication version here, but max LE if. So rewrite max LE if, there we go. I mean, it's exact max LE if, isn't it? So we could solve it with library search. And library search tells you it's max LE if, but what I'm saying is, after a while, when you get the sort of the hang of these things, you can start guessing what the names of the lemmas are. Right? There's only a few tactics, but there's thousands and thousands of lemmas. We've seen most of the tactics we'll be using in this course already, but there's many lemmas. You see, again, if I had to guess what this would be called, this is going to be called either abs LT or abs LT if. Let's find out with library search. There, it's called abs LT. Now this one, again, So norm num certainly wouldn't do this one. Well, I guess it wouldn't. Norm num. Yeah. I mean, one of the reasons it might not do it is because we're going to have to use this hypothesis. I'm not sure if norm num uses hypotheses. But the linearith tactic certainly does hypotheses. It proves, arithmetic equalities and inequalities, but it will assume hypotheses as well. So linearith should solve this one, which it does. But also, my guess is that this is going to be in the library. So there we go, half pos, exact half pos LE. So what does half pos say? Half pos says, if alpha is positive, then alpha over 2, then half of alpha is also positive. So that's done this one. And now this one, this is going to be called add LT add or something. Let's try library search. There we are. Yeah, we go. It's called add LT add. This one might not. My guess is that library search will fail for this one. Yeah, it's thinking for a long time. There we go. And now it's failed. So, yeah, I mean, one could argue that that should be called third pos and it should be in the library. But because this is an inequality which can be deduced relatively straightforwardly from other inequalities, my guess is that linearith will solve this one. So there's linearith solving that one. And similarly here, you see we had add LT add, right? We could apply, you see, might think, oh yeah, we've had this before, right? This is less than this and this is less than this, so the sum of those is less than the sum of those, right? So it's going to be exact add LT add, and then H1 H2. And this somehow has failed. And it's failed with a slightly obscure error as well. It's like, it says H1's got the wrong type. It was expecting H1 to be a proof of A plus B plus C is less than X. So what's actually going on here? Remember the brackets are there, right? No brackets are printed, but it's A plus B in brackets, plus C in brackets, plus D. And add LT add, the thing we did up here, I guess we've got, so it's expecting something plus something is less than something plus something. And it looks, well, is the left hand something plus something? Yes, it's A plus B plus C plus D. So it wants to prove that A plus B plus C is less than X, and it's not what we have, right? You see, add LT add, let's do this. Have H3 is add LT add. And you see H3 is not exactly equal to the goal, right? I mean, obviously it's sort of completely logically equivalent, but modulo some issue with commutativity and associativity. You see, and Lean is extremely picky, so Lean won't let you use add LT add here. So I guess we could rescue this proof because H3 is very close to the solution. So for example, we could do this. So let me do it in sort of the long. Let me show you quite a long way of doing this. The issue is that A plus C plus B plus D in brackets is not equal to A plus B plus C plus D by definition. It's equal because of a theorem. So we could make that theorem have H4. So was it A plus C plus B plus D equals A plus B plus C plus D? There. That's what we want, right? And then we could prove that with the ring tactic, because that's just an equality. That's an identity in ring theory. So now H4, so now you see we can rewrite H4 at H3. At H3. And now H3, oh no, what have I done? I rewrite H3 for H3, there we go. And now H3 says exactly what we want. So we could do exact H3. So that would be one way of doing it. Rewrite, and then, or alternatively, instead of, we could do assumption, right? Because H3 is one of our assumptions. But rewrite then assumption, there's actually a tactic that does that, RWA. There is the rewrite and then assumption tactic. But it is still a bore that we had to introduce this new hypothesis to do it. If we insist on proving it with add LT add. So another cool way to do it would be, we could argue that H3 is very nearly equal to the goal. And so why doesn't Lean just replace the goal? Why don't we tell Lean that the goal is essentially H3 and just give us, I don't want to write H, it's a bore to write H4 because it's sort of quite a long thing to write. So why don't we tell Lean, listen, the answer is H3, except it's not quite, so why don't you just tell us exactly, which bits are missing. So we could do convert H3, which will do its best at trying to work. Let's get rid of this stuff. It'll do convert H3, which will do its best at sort of saying, well, okay, you say that H3 is the answer, but the H3 is not the answer, but you're telling me that H3 is supposed to be the answer, so let me guess what you mean, right? And so it guesses, well, if A add B equals A, and if D is B add D, then everything is going to match up. But I mean, you see, converter's done too much. It's like, well, look, this adds up to this, and this is A plus B plus C plus D, and this is A plus C plus B plus D. So maybe the user is claiming that A plus B plus C equals A plus C. Its converter's gone too far. So let's tone it down a bit. Convert using, let's say 1. And there we go. I've said to convert, look, it's nearly the answer, but just like the first time you see some things which aren't actually exactly equal, then give me that as a goal instead. And so now sort of we can just solve that using the ring tactic. There you go. So goals accomplished there. And so of course we could even, now we don't even need to use H3. We could do this, right? There. So there we go. So now we've got a two-line. So now we've got a two-line proof. So that's looking slightly more respectable. But we had to rely on the fact that add LT. We had to rely on the fact that we knew about add LT add because we'd just seen it up here. So we can do even better because again, this is just an inequality which follows from a bunch of other inequalities which are hypotheses, and that's what the linearith tactic was designed to do. So there's a one-line proof of this example. Okay, so there you go. That's the end of that, and thanks for watching.